at three different varieties of collision. In the first set, we saw collisions that had equal mass. I want to know, what did you observe for the collisions that had where the objects had equal mass? What'd you see? Okay. Okay. So object that was moving stopped, and then the other one started moving. Moving object stopped. Other began moving. Other things you guys saw or specifications you want to add to that? Okay, so velocity appears to be equal between the two cars. Say again? Okay, complete transfer of energy. And I'm going to specify kinetic energy. Of kinetic energy. Anything else? Anything else you guys had for these equal masses in their collision? Okay, I want to elaborate on what Stefano said. It's not just appears to be equal, they actually are equal. Okay, that's not just an appearance. All right, so next setup, we had more mass on the target, so heavier target. Okay, what did you notice with the heavier target car? What was similar to the previous one? What was different about it? Okay, so after collision, move in opposite directions. Collision, move in opposite directions. Anything else? Heavier one moved. What do you mean by moved most? Okay, so the target one ended up moving faster. Okay. We can recreate that real quick to double check that. All right, looks good. Anything else that we should add to this heavier target one? What do you mean? Okay, so as opposed to in this situation, okay, I'm not going to say, how do I want to phrase this? Obviously, they both push on each other equal amounts because that's Newton's third law. For every force, there's an equal opposite reaction force. But I will say that there's more recoil on the moving one, or recoil on moving one. Anything else? Okay, then our third setup, the heavier one was moving. What did you see that was unique in this one? Okay. Weighted car kept going forward. Okay, what else? How did their velocities compare? Which one was faster? Okay, lighter one was faster. Was it faster than the moving car's original speed? Don't feel so. Okay. All right. So each of these three collisions we categorize as what we call an elastic collision. Elastic collisions are characterized by two things. First of all, the objects bounce off of each other. Objects bounce. And the second part is that in a perfectly elastic collision, kinetic energy is conserved. Ke is conserved in a perfectly elastic collision. Now, I do want to clarify that I'm saying kinetic energy is conserved, not just energy is conserved. If I were saying energy is conserved, well, that's everything always, no matter what the situation. Here I'm saying specifically kinetic energy is conserved, meaning that everything that was kinetic energy at the beginning doesn't change to gravitational or work or anything else. It all stays as kinetic energy on one of the two objects. Okay? Clarifications or questions on this? The first one we saw was, again, equal mass. What was unique to that collision? What did you see? They're stuck together, all right? Somebody got something more for me. Okay. Any more? By how much? Hard to say. Okay. Slowed down. Anybody else? Say again. Yep, it was actually exactly half. Slowed down by half the original V. Anybody else? Something you observed with this one? Okay. 5. Again, heavier target. What'd you see? Okay, so they stuck together. Okay. Not exactly a fourth, but it was definitely less than half the speed. Less than half the original speed. Anything else? Okay. Then let's look at our last one, the heavier moving again. What do you have here? Should I just write stuck together just automatically? Okay. How'd the velocities compare? Slowed down, but more than half. Okay. Slowed down, but more than half original velocity. That's a O. All right. Anybody have anything they want to add to any of these? So these bottom three are what we call inelastic collisions. Inelastic collisions. An inelastic collision is a collision in which objects stick together and kinetic energy is not conserved. Objects stick together Ke is not conserved. All right. So as it stands, we've got two options for types of collisions. We've got elastic collisions, we've got inelastic collisions. Reality mostly occurs on a spectrum somewhere between these two things, where perfectly elastic collisions actually almost never exist. Like to create one, we'd need to have like a maglev system with in a vacuum tube. Then I could probably create a perfectly elastic collision, but that's highly improbable. So perfectly elastic collisions almost never exist. Um, the AP students were able to determine that ball bearings have collisions that are like 95% elastic. So most of the kinetic energy is still there, and saying it's an elastic collision is pretty reasonable, but it's not perfect. Inelastic collisions are, of course, the other end of the spectrum, but reality exists mostly in between the two. Sure, we can get inelastic collisions. Things stick together all the time, and some of the kinetic energy is lost. But most of them are going to exist somewhere between these two things. Okay? We can classify every collision as one of these six. So what we're going to do next is I'm going to do a handful up here. I want you to identify which one they categorize as. Helps us dictate exactly what's going on between the different objects and shows that there are a lot of collisions that are actually very similar to each other. So now we've got an identity for each of the six different possibilities here. The reason we did this is anytime you're doing a practice problem or a lab question, you should be able to identify your collision as one of these six. And whichever one of these six it's looking like, you should be able to recognize, well, it should exhibit these traits. If it doesn't exhibit these traits or give you this kind of answer, you did something wrong. Okay? So you should be able to identify every problem we do as having one of these six types of scenarios. Okay, so momentum. Suppose we should get an actual definition for it. Two words I want to avoid using when talking about momentum. I don't want to use the words force or energy when defining momentum because momentum is a property unique on its own. It's not like force or energy. Okay? Momentum is simply a product of mass and velocity. A product of mass and velocity. We can say it is a strength of motion, a strength of motion. Notice how I did not say a force of motion. That would be incorrect. Okay? It is a strength of motion, product of mass and velocity. Now, calculationally, we can say that momentum is equal to mass times velocity, where if we're talking SI units, mass would be kilograms, velocity would be meters per second. However, momentum does not have its own unique derived unit. It is simply kilogram meters per second. This means that as long as any of the units we're using on a problem are all the same, it really doesn't matter what we're using. If we want to do a whole problem in grams, centimeters per hour, go for it. If you want to do a whole problem in stone miles an hour, sure, why not? Momentum will still work out just fine. We don't have to do any conversions, as long as all of your momentums in your scenario agree. Okay? Now, in ninth grade physical science, you probably talked about momentum, and you probably calculated momentum of a moving object, or you calculated the mass based on knowing the momentum and the velocity of a moving object, all of which was horrendously pointless, because momentum on its own is a worthless concept. Momentum as a conserved property is very useful. Momentum exists simply for us to understand how collisions occur and how we can predict what happens during a collision. So conservation of momentum. Okay? Conservation of momentum basically plays out like conservation of energy. Momentum cannot be created or destroyed, but can be transferred. Momentum cannot be created or destroyed, but may be transferred. Mathematically speaking, that says that the sum of the momentum in one dimension initially is equal to the sum of the momentum in the same dimension at the end. Momentum, unlike energy, is a vector unit, meaning that dimension matters. And you can have negative momentums because you're going to have velocities that are going in opposite directions. So direction and dimension matters because momentum is vector unit. Another way to write out this equation is, of course, P1x plus P2x, etc., equals P1x final plus P2x final, etc. Questions to this point? Okay. Quick example then for, let's go an inelastic collision. We all know that they're going to happen right along 25th as soon as more snow falls. Somebody's going to rear end somebody along this coming out of school. Couple of different things about cars. Older cars, when we're talking like the 40s and 50s, were built on largely steel frames, and we saw more elastic collisions where the cars bounced off of each other. However, as we've made cars safer and cheaper, we see a lot more plastic pieces on them. And cars, when you rear end them or you get into wrecks, they immediately crumple and basically get destroyed way faster. Okay? This is done not just to make the cars cheaper, but it's actually also safer. And we will see that that is safer using impulse and momentum a little bit later. But for right now, let's just take an example of, I'm going to pick on Mackenzie. Is there an A in there? I did have it right. Okay, good. Yes? Is driving a 1,000 kilogram vehicle at 30 miles an hour when I'm going to pick on James. Rear ends her at 40 miles an hour in an 800 kilogram vehicle. We're going to assume the two vehicles are newer. They crumple at the ends and get locked together and continue moving after the collision. We want to know, how fast do they move post-collision? How fast do they move post-collision? Okay. So, solving this one, I'm just going to use conservation of momentum. I'm going to show that the momentum of the first object plus the momentum of the second object is equal to the momentum of the first object final plus the momentum of the second object final. Momentum being m times v, I've got 1,000 times 30 because it's momentum. I'm going to use miles an hour. Why not? Plus 800 times 40 equals momentum of the first car, so 1,000 velocity final plus 800 velocity final. How are these two velocities going to compare to each other? They're going to be the same. In any elastic collision, we identified that the objects stick together. If you're stuck to another object, you're going the same speed. Meaning that this is really 1,800 VF. This is going to be 32,000. And this is going to be 30,000. Okay. Solving this, I get 62,000 equals 18,000 VF, and VF is now equal to, anybody have a number for me? It's like 3.3, 3.4, or sorry, 33, 34. $3.4? Oh, oh, I did? Where? Ah, thank you. I knew my answer shouldn't be like that. So it's 34.4 miles an hour. Okay. So James slows down significantly, and Mackenzie speeds up by about 4.4 miles an hour. Okay. Questions about solving for this? Yeah. Because in an inelastic collision, they stick together. Just kind of like the needle and the clay, they stuck together. And actually, we do see that with how crumple zones work. And usually the cars aren't exactly the same height, so one gets hung up on the other somehow. So in a good higher speed collision, yeah, they definitely happen. In slow ones, especially where people are paying any kind of attention and hit the brakes, they're more elastic. But for higher speed collisions, yeah, they definitely occur inelastically. All right, we got about 3 minutes left. We'll work on some examples of this tomorrow.